Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. And this is a continuation of a lecture for intermediate algebra on the quadratic formula. In this part of the lecture, we're going to talk about complex numbers, which is really the first introduction to them because where you really truly run into them is when you're solving quadratic equations. And then in future applications, you tend to run into complex numbers. So this is the part C of this lecture series. Before we go any further, I just want to remind you of the quadratic formula, that we're given a quadratic equation of the form ax squared plus bx plus c is equal to 0. And given that quadratic equation, the solution is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. And we're going to use that to solve a very specific kind of quadratic equation. We'll go ahead and solve x squared plus x plus 5 is equal to 0. And as we've mentioned in previous video lectures, first thing I'm going to try to do is factor this. So I'll take a look at this and see if it factors. X times x would give me the x squared. And the only way I can get two numbers that multiply to 5 is if this is 5 and this is 1. However, you could already see that this is not the way it's going to factor because this would give me a 6x for the middle term. So I already know this is not going to work. So it looks as though we're going to have to jump right into the quadratic formula here. The a for this is 1, so that's the coefficient of the x squared term. The b, which is the coefficient of the x term, is 1. And the c, which is the constant term, is 5. Using the quadratic formula, we get x is equal to the opposite of b plus or minus the square root of that b being squared minus 4ac all over twice the value of a. We'll go ahead and simplify this down. This is negative 1 plus or minus the square root of, and you'll see that underneath the square root I have 1 minus 20, or in other words a negative 19, all over 2. And this should be one of the first few rare moments where you have encountered a negative underneath the square root. Up to this point in mathematics, a lot of people say that have probably lied to you and told you that this number doesn't exist. This number does exist, actually. This is just a special kind of number. Having a negative underneath the square root causes us to basically have to invent a new number system. Now, this number system that we're about to create was not formally defined until the mid-19th century. So it's a fairly recent addition to our mathematical set of objects. So we're going to start with a few definitions here. The first one is the definition of the imaginary unit. So the square root of a negative 1, the simplest square root involving a negative as the radicand, the square root of negative 1 is defined to be I. So from this point forward, every time you see I, you should think, oh, that's the square root of a negative 1. Just a symbol for it, just like pi is roughly equal to 3.14 dot 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 dot. Okay, so it turns out that I is just our standard notation for the square root of a negative 1. Well, this allows us to really introduce a whole new number system. So I'm going to define first what a complex number is. A complex number is a number of the form a plus b times I, where a and b are real numbers. A and b are real numbers. And I just want to start introducing you to correct mathematical notation. A and b are real numbers. A shorthand for that is this: a and b. This means a and b belongs to, and that R right there stands for the real number system. So just to let you know that a and b are real numbers. For example, some examples of complex numbers are like 3 plus 2i, or pi minus 1.1i, or 3/7 minus 2/3 times I. All of these are complex numbers. And in fact, it's a whole new number system. Remember the number systems, if you view past through my previous lectures, we had these number systems, the natural numbers, the whole numbers, the integers, the rational numbers, the irrational numbers. All of those sets, specifically the rational numbers and the irrational numbers, when we combine them and grab them and put them in a container, we call that the set of real numbers. But this is a new set of numbers here, the complex number system, and it's just a set of all numbers of the form a plus bi. So going back to our example, how could I write this as a complex number? Remember, it has to be written as a plus b times I, where a and b are real numbers and I is just the square root of a -1. Well, here's how it's done. I'm going to switch my pen color here a little bit. And first thing I'm going to do is break up this fraction. That fraction can be written as -1/2 plus or minus the square root of a -19 over 2. And this comes from a theorem you learned a long time ago. If you have a over b plus c over b, that's equal to a plus c over b. And all I did is I actually worked from this and split it apart. So it's a over b plus c over b. So in other words, it's -1 over 2 plus or minus the square root of -19 over 2. And now we'll go ahead and write this as -1/2 plus or minus. This can be written as the square root of 19 times the square root of -1 all over 2. But now I know the square root of -1, that's just I. So this can be written finally as -1/2 plus or minus root 19 over 2, and that's being multiplied by I. That is written in complex number format. What's interesting about this, if you just look at the basic form, ignore the fact that we have 1/2 and root 19 over 2's. It's in the form of number plus or minus some other number, I, which is very interesting. So I have a solution to this quadratic equation, and the solutions are -1/2 plus some number I and -1/2 minus that same number times I. This plus or minus business introduces an idea called a conjugate. Now, often I will see it written in textbooks that authors will talk about this as complex conjugates, but I'm just going to call it a conjugate. The conjugate of the statement a plus bi is a minus bi. Really, all we're saying is that if you want to find the conjugate of a complex number, you flip the sign in the middle. Same thing, if you have a minus bi, the conjugate is a plus bi. So you're just flipping the sign in the middle. And what's interesting about conjugates is that, and not only just conjugates, but conjugates and solving quadratic equations, is that when you solve a quadratic equation, if you have a complex number solution like this, then you also have its conjugate as a solution. And that's actually a theorem, so let me write that down. So if a plus bi is a solution to a quadratic equation, then its conjugate, a minus bi, is also a solution. By the way, this also holds if a minus bi is a solution, then a plus bi is also a solution. Now, I want to just state right now that the point of this complex number conversation is not to get you to be an expert with complex numbers. Not at all, in fact. All I want you to be able to do is recognize a complex number solution to a quadratic equation. So let's go ahead and try to solve this quadratic equation right here and see what happens. First thing I'm going to do is see if I can factor this. I immediately can already see it's not going to factor. Two numbers that multiply to 12 is either 1 and 12 or 12 and 1. 2 and 6 or 6 and 2. 3 and 4 or 4 and 3. And if you check each of these to try to make a combination of them to become 3, well, I know 2 and 12 and, or I'm sorry, 2 times 12 is 24 and 1. 24 and 1 is, there's no possible way there. 2 times 1 is 2, and then 12 times 1 is 12, so 2 and 12, no possibility there. 12 and 2, again, no possibility there. 4 and 6, no possibility there to get to 3. 8 and 3, no possibility. And 6 and 4, no possibility. So just kind of quickly checking through, there's no possibility to factor this. So I'll just erase all my tries. And now I know I'm going to immediately go for the quadratic formula. X is equal to the opposite of the b term plus or minus the square root of that b term being squared minus 4 times the a term times the c term all over 2 times the a term. Again, I shouldn't be using the word terms here. It's the a, b, c, but I said it, so I have to kind of stick with it. So that's negative 3 plus or minus the square root of, let's see, I have 24 times 4, which is 96. And so we have 9 minus a 96, which is a negative 87, as I think about it. Yeah. All being divided by 4. So at this point, I need to really write this in terms of a complex number. So I will do this negative 3 plus or minus. I'll write this as a square root of 87 times the square root of a negative 1. As you can probably see, negative 1 times 87 is going to be a negative 87. So that is proper. And I could rewrite this as negative 3 plus or minus I times the square root of 87. Now, what I want you to recognize here is that I'm writing the I in front of the square root. The reason why is just a good habit to get into. Writing an I at the back end of the square root sometimes fools people into thinking that it's underneath the square root, and it's not. An I never goes underneath the square root, so that it just sticks out front. It's just easier, better notation to leave the variable out front, even though it's not a variable, but leave the letter out front. And now I'll write this in complex number form. That's a negative 3/4 plus or minus root 87 over 4, all being multiplied by I. And that's a complex number form. And notice that we actually do have the solutions are conjugates. In other words, the solutions are a number plus root 87/4 I, and the other solution is actually its conjugate, a number minus root 87/4 times I. Very interesting result. But it's always that way with complex numbers, that the solutions, complex numbered solutions, come in conjugate pairs. As a very advanced problem when you're dealing with complex numbered solutions for quadratic equations, you could consider this problem here. Let's suppose that we know a solution to a quadratic equation is 2 minus 3i. So we have a quadratic equation and we happen to know that x equals 2 minus 3i is one of the solutions. Can we find the other solution without any work, basically? And the answer is yes. According to the conjugate pairs theorem, if 2 minus 3i is a solution, then its conjugate, 2 plus 3i, is also a solution. So these are our solutions. And now we want to write a quadratic equation having these solutions. And now this is kind of the challenging part initially for students. I'll show you how it's done by taking a side example here. So let me hop over and just say, well, suppose we had a quadratic equation that had these two solutions. Well, that would imply that x minus 2 is equal to 0 or x minus 3 is equal to 0. Right? Because that's me subtracting 2 from both sides of this equation and 3 from both sides of the second equation. And now since either the first or the second object is equal to 0, when you multiply these two things, their product has to be 0. So when you multiply these two binomials, the product must be 0. And now you can see I could just distribute this out. I get x squared minus 5x plus 6 is equal to 0. And that's the quadratic equation right there that has x equals 2 and x equals 3 as its solutions. So we're essentially going backwards. Normally when we solve a quadratic, we try to factor it and then we solve those factors, right? So in the case that we're dealing with in this problem, we're going to do the same thing. X equals 2 minus 3i implies that x minus 2 plus 3i is equal to 0, and x minus 2 minus 3i is equal to 0. So if both of these statements are equal to 0, then their product must be equal to 0. And now you can multiply this out. There's a couple ways you can multiply it out. You can either, well, there's a lot of ways actually you can multiply this out. You could either stack it or you could distribute. I'll go ahead and distribute just to show how this works. It's going to work just like regular distribution, so don't be too intimidated. We'll have x times x times a negative 2, and then an x times a negative 3i. And then do this in orange, we'll have a negative 2 times x, a negative 2 times a negative 2, and a negative 2 times a negative 3i. And finally, we'll have, I'll do this in bright green, 3i times x, 3i times a negative 2, and 3i times a negative 3i. So here we go. Let's go ahead and do this. We'll do the red stuff first. X times x gives me an x squared. X times a negative 2 gives me a negative 2x. X times a negative 3i is a negative 3i times x. Now we'll do the stuff in orange. Negative 2 times x is another negative 2x. And negative 2 times a negative 2 is a positive 4. A negative 2 times a negative 3i is a positive 6i. And now we start going to the stuff with green. 3i times x is a positive 3ix. 3i times a negative 2 is a negative 6i. And finally, positive 3i times a negative 3i is going to be a negative 9. I times I is an I squared. We'll talk about that in a moment. But let's at least combine like terms. I have an x squared. Let's see, I have a negative 2x, lose another 2x, gives me a negative 4x. I have and let me cross out the stuff that I've worked on here. I have a negative 3ix, but I'm adding back a 3ix, so those two cancel. I have a positive 6i, but I'm losing a 6i, so those two cancel. I have a plus 4, so let me write that down. And then I finally have a minus 9i squared. Now there's something about the I squared that you should know. If I is defined to be the square root of a negative 1, if we square both sides, I squared will be, well, negative 1. It's the only number that when you square it, it becomes a negative 1. And that's a super important fact. So what I'm going to do is replace this I squared with a negative 1. So this will be x squared minus 4x plus 4 minus 9 times the negative 1, or in other words, plus 9. That's positive 9 plus another 4, that's 13. So the answer is going to be x squared minus 4x plus 13. This is the quadratic equation. Well, actually, that's not that's near to the quadratic equation having those solutions. Technically, the quadratic equation having those solutions is going to be x squared minus 4x plus 13 is equal to 0. The solution to this quadratic equation is going to be 2 minus 3i and 2 plus 3i. A lot of work to that, but well worth it. You get a nice looking quadratic equation in the end. Very nice tactic.